Hey, so welcome to today's lecture on neural networks and deep learning. What the plan is for today, we will continue with the self-attention and mainly focus on two things there which we haven't covered there. The one is positional information, and then the second is on trying to make it a bit more efficient. And that is then also a good next step to what we'll cover afterwards. We'll talk about so-called state space models, which will remind you, I guess, again about RNNs, but there are some interesting other type of sequence models which try to address some of the computational problems here. And there will be then some of the last type of architecture that we will cover in this field of different sequence models. We'll finish up on Tuesday then with broader things on comparing again the different types of sequence models. But we'll start again now with this type of positional information. Why are we covering this part? So therefore, it makes sense to think about how different positional information are encoded in the different networks. And I have here a comparison between the two. On the left, you see an RNN, and here you see a self-attention network, so one layer of self-attention. Now we have the sentence Mary kills John. There's like some input embeddings, and you might have now, you calculate the hidden states, you get a hidden state here for Mary, you get one for kills, and you can get one for John. And similarly, when you do self-attention, you also calculate the three hidden states, and you calculate one for Mary, you get one for kills and one for John. Now the question is, if you're not having the sentence Mary kills John, but you have the sentence John kills Mary, can you say anything about the hidden states you'll get in that case for the RNN and for the self-attention? Does anybody have an idea how these will be looked? Yes?
For RNNs, this dependency is probably visible for the model because it's dependent on each other. Well, for self-attention, there's no information on that.
Exactly. So if you're trying to see that, we're not really sure how this looks. But the representation of John here is different from the representation of John you have here, as well, of course, also as the one for Mary. The same for kills, as well, although it's at the second position, these representation and these representation are both different because they encode that previously we had Mary and previously we had John. And the same for Mary. If we're now looking here, for Mary, the representation is now on the third. So you see the sequence we have is different. It's not that in self-attention, the hidden sequence is the same for Mary kills John and John kills Mary. But the representation for John is exactly the same in Mary kills John and in John kills Mary. Because how it is calculated, if you look about what we did is, we did calculate the weights. In both cases, the weights will be the same because you do compare the query and the key. And there's nothing about the position between them in there. You just do this comparison. You get a scalar which you multiply with your value, and then you do the weighted sum. There's nowhere in there that there's some positional information in there. So in the end, you will have a different sorting of the sequence, but the elements of that will be all the same. That's of course not super helpful because what Mary means in this sentence is very different from what Mary means in this sentence. So the representation should also be different. And if we think about it, it's quite probable that this will not be a very successful model. Because in the end, I mean, one thing now, what can you do in the end if you would do now average on top of that pooling layer to do a classification? These two would be exactly the same. So you will not be easily able to really build a strong model if you're mainly ignoring the positional information. Because in a lot of scenarios, positional information are, of course, essential. Here you see it nicely, but also if you think about audio, in all these, it's of course important in which order the information is. which of course now is a bit maybe disappointing. We are talking about this great Euro architecture, and now it should be that, yeah, mainly it can't even handle any dependencies, but it's mainly what people in natural language processing call a bag of words representation, meaning, yeah, you just put your words in the bag, you can shuffle them, and it doesn't really matter in which order they are, they're just somewhere there in the bag. So this seems not to be the best solution. And you might already think that this is not how everything about self-attention network, because if that would be all, it wouldn't be strong. So it's very nice in one way that our calculation only depends on the inputs, because that means we can do parallelize all the calculations. Then we said it's a very nice thing about self-attention that we can parallel process all the inputs and calculate all the hidden states. But that also means if we're just applying it directly, that these representations will be the same, and therefore we won't be able to do that. So we need somehow a different way of handling that, because otherwise our model wouldn't be really strong. And in the title we had before, I already hinted to a solution. So the idea we're going is, okay, we can't easily model positional things in our architecture. So our architecture is just, we're processing everything in parallel, so these aren't there. But the first and easiest thing we can do is, now maybe we can just put it in the input already. We are claiming here that the input of Mary here and the input of Mary here is the same we put in the network. But if you somehow mark here already, this is Mary at the first word position, and this is Mary at the second position, then you have this information already in the input, and of course, then your computation later will be different, and the hidden state won't be the same again. So then you don't need to reprocess that these are the first position and the position. If you once put it into your feature space, into your representation, it's in there, and then the model can use it. The problem was that in the initial version, these Mary and this Mary is the same. So it's just indicating one hot encoding. We had that, this is Mary, but it's not indicating, oh, it's Mary at the position X, Y, Z or something. So the question is then, of course, how can we put somewhere there information about the position, that this is word number 7 or this is word number 5? Any idea of how to do that? Yes?
Trigonometric functions.
That's already how it's done in the transformer. Maybe do you have also a more simple idea? What would be the first, if you have, for all of you who hopefully maybe haven't heard about it, you should still, based on what you learned in this lecture until now, you should have an idea what you could do. Yes?
We could coordinate our inputs with the positional value.
Yes, exactly. So that's learn positional embeddings, and that is somehow one thing we could do. So let's go through that, and then we'll come exactly, you're right, the trigonometric function is then what we're doing, and we can also explain then why that might be a better solution then. But maybe the easiest thing would be, so this is how you put in variables normally. So we said words are put in as one hot encodings, as other categorical features. So you're putting, this is word number 4, this is word number 3, and this is word number 2. And then you have here these embeddings, so just a feed-forward layer which learns these types of embeddings, and then you can, based on that, now do your self-attention on top of that. So you can take now these 3 vectors, apply self-attention to that, and learn it. And this will be your word embeddings that you have. And now you're right, what you can do is, okay, Mary, that this is Mary is one information, but I know more about this event. I know also this is at position 1, this is at position 2, and this is at position 3. So we can also encode this information. And of course, there's again different ways we could do it as a number, but maybe it's reasonable to do it as a categorical value also. So we do a one-hot encoding for all of the positions. And then it might be reasonable to again learn an embedding, learning that, okay, this somehow means that we're currently at position 1, this is a 2, and so forth. And then, as you correctly said, we can just concatenate them and put them together. Again, that is the very nice thing about neural networks. There it's very easy to fuse information where we now want the content and the position, and I mean, these are both represented as vectors, so I can just do concatenate the vectors, and then we have everything that we can do there. So now you have these vectors. There are these three vectors, and I think hopefully it also gets very clear again. If you're now doing that, you will have different values for whether this is Mary kills John or John kills Mary, because these vectors are different. If John is at the first position, you would have this vector, the blue part, and this purple part connected, so it would be a different one. And therefore, also all your computation about the self-attention would be in there. So you mainly does your self-attention no longer on Mary kills John, but on Mary at position 1, kills at position 2, and John at position 3. And then if you compare, you're no longer comparing how important is Mary to understand John, but your question is how important is Mary at position 1 to understand John at position 3. And you then implicitly see how you can learn that maybe position 1 is more important to understand position 2 than position 349 or something like that. Yeah, this seems good. And I mean, it's not only like now because it's easy and that's why we're doing it. There are some systems which exactly do this and use these types of learned events. However, we're just already heard there's also other ways of doing that. And so the question is why? And do you have any idea what might be a problem in this type of scenario where you learn these type of learned embeddings? Yes?
It would kind of kill the idea of variable size inputs. Because if the sentence length is not the same, or the input size is not the same, or longer than the one which is learned, then it would no longer be possible to encode that position into the parallel encoding.
That is one point, and that's completely right. So if in your training the longest sentence is 325, then you can only are able to encode sentences until 325. And if you get a sentence now with 326 words, then the last word somehow doesn't work. However, there is, of course, I mean, I wouldn't see that as the only biggest problem. There's other limitations. I mean, it also has to fit into your memory, and you can make your training data in a way that you'll have a long sequence in there and that you have learned. So it's a very good point. It's one point, but there's also a second one. So even if you're saying, okay, that's a limitation I take into account, I now only can process words, sequences up to 225 words, and nothing else might be for some application might be good enough. There's still one problem or like one thing which makes this maybe not perfectly good. Yes?
It's a no-way shift invariant, so it's very important that the word has to be Mary has to be in the first place, and that means a completely different thing if we have Mary plus John at position 100 in our text.
No, I mean, your top embeddings are different, but hopefully the model learned that in order to understand Mary, it has first to focus on the lower layers, on the lower dimensions, because this Mary part will be always the same. And then it just has to, okay, maybe ignore the position. I mean, you're going in that way in the right direction is like, yeah, maybe then it doesn't really understand anymore, like if it's Mary kills John or John kills Mary. But I would understand that. But it goes a bit in the right direction about where it is. It's not that the positions are no longer in there. Yes?
Maybe not correctly learning the syntax of the language of learning. Because if the position is hardly included into that, it does not learn that words can have a different meaning in different positions of a sentence.
That is somehow true for all positions, because we will always somehow encode the position. So it's maybe surprising that it's learned and that sometimes 2, 3, and 4 I mean, depending on what before, it doesn't matter if it's like one position to the right. Then you hopefully learn a bit by having these on. There's one thing about the frequency. Yes?
Higher numbers will get used probably less.
That's the other problem. So you will very good learn a good embedding for 1, 2, 3, for 55 maybe also, but 221, there will be very few sentences with 221 words, and even if you enforce it to be there at least once, still if it really learns it well is not a problem. So you mainly learn the beginning of the embeddings, and the later embeddings won't be learned that good. So this is a bit the two disadvantages. You have a limited length, and you have a high number for high number, it's rarely occurring. And that's why, like, at least the most common one in the early works of attention is what is called the trigonometric functions, where the idea is we're taking a function which is just going for a very long sequence, and then using that to again do the change. So this time we don't have explicit embeddings. So what we're doing is we're taking our one-hot encoding, and then we are calculating word embedding. And now the positional embeddings aren't learned. We're just fixing them. We're just fixing what does it mean to be at position 1, 2, 3, and so on. And then the model has to learn everything around it to fit to this positional embeddings. How we're doing is we are taking n different trigonometric functions. So one for each dimension of our word embeddings, and then we're putting them on there. So you have a large wavelength at the top, and then they're going down to always smaller wavelengths as you see. And then you're calculating them, like the values of these different wavelengths at the different position. So at position 1, the sinus will all be 0, and you have cosinuses which will all be 1. And if you then go one step further, you see that they are different. There's the short ones where you're already nearly at 1 maybe, while the longer ones you're still lower, and so on. So by this one, you're now having a vector which you can calculate for any position. It will always have values between +1 and -1, and it will be different for each position. Depending now, of course, on your on the longest joint sequence, and at some point all these frequencies might be again the same, but if you choose your size of your wavelengths well enough until things repeated are so far that it doesn't really matter anymore. And then you take them and add this value just to your vector. So you have now a second vector, you add these two vectors up on each other, and that is then your value, and then you can calculate with that one again, obviously. So this time it's not that we are learning what is a good representation of the position, but we're like somehow fixing it. We're saying this is the representation of position 1, 2, 3, and 4, and we're defining it in a way that it's easy to extend it to any type of length of a sentence. That of course only works since we are having here embeddings which are learned, so the word embeddings, and the word embeddings can be learned in the way that they are playing well with our positional information. So that is important. That, I mean, you can't of course combine two things which are not learned. Now the embeddings have to be a bit adapted to fit well with the positional encoding, so that not like important information gets thrown away. If you would now encode something really important in this dimension, and then somehow only put it in this dimension, and then somehow it gets always removed or so, then it might be a problem. Good. Yes. And D model is here. Oh yeah, D is the dimension we are currently in, and D model is the size, so how big your dimension is. So if you have here would be 3, in reality it's 500 or something like that. And with this you're achieving that you always are taking a different step size here.
So it's the size of the dictionary.
No, D is not it. It's like no, it's not the dictionary because it's already on the word embedding size. So this is a dictionary size. You have a one-hot encoding. Then you do your word embedding. Here you're going from a dictionary of 5 to 3. In reality, you'll go from 20,000 to 1,000 maybe. Okay. And then this D model is 1,000, and D is your current index UR. Okay. Any more questions? Good. One nice thing now we'll see is, oh, this can be easily now extended also to other structures. Now we have done it only for sequential data. And we have seen already how things are done in the CNN TDN thing there. We also could easily extend from sequences to 2D. In the RNN case, it's a bit more difficult. Does anybody have an idea why it might be a bit more difficult? There is solutions to it, but it's generally more difficult. I mean, you have a direction, so it's maybe a bit like, do you first go in the X or the Y direction? How do you connect? It might not be as clear. In the attention, you only look in the attention, and in the CNN, you only look at your input, and you're not looking at other things in the same layer. And if you now have a 2D in the sequence, it's clear that you maybe go from left to right, but in a picture that gets more not clear in which direction you go. Here it's quite straightforward in the self-attention. So sorry, what we can do is we can also do this in a multi-dimensional case. So what we then do is, like, we have our image which has size h times w, and we are making them into patches which typically have size p times p. So we are slicing the image into these different things where we each treat as one of our units. And then we can put them just into a sequence where then we have here our input. The number of the dimension here is, for each pixel here we have C values. So for example, in RGB you have 3 values. So here you have then for each one p squared times c, because the size of this one is p times p. So the dimension of this vector here is like p squared times c, because you have for every pixel 3 different values. And then here the size is h times w divided by pair square. So these is how many elements you have. And what you have done mainly is you take your picture, you have put it into a sequence here. And then you can again process the sequence the same way. There's, of course, now different ways of how you implement your positional information. You can learn then again embedding for each of your vector. You can look if you always do it the same. You can even just do positional information normally and learn it, but you might want to encode information in both dimensions that you know whether it's a neighbor in the X dimension or the Y dimension. But in generally, it's exactly working the same. And afterwards, we're processing everything as just a set of elements, as we have seen in the self-attention. So it doesn't really matter whether this set is 1-dimensional, 2-dimensional, or anything. The only thing where positional information, which are different in a 2D and 1D case, is in the encoding. So you only have to somehow change your encode it then, because afterwards you anyway do the all-to-all attention. And there it doesn't matter how they were arranged before. Good. Any other questions to this? And then we want to go to 2 more, like advanced now, positional information. And here the main idea is, at least in text processing, it might be more important to have the relative information than the absolute value. So until now, although we are able with the trigonometric functions, we are able to like do any type of length, but it might not be as important to know whether the word is in position 101 or 125. But in order to understand Mary Kills John, it's more important that it's like, oh, it's before or after, or it's like 2 words before or something like that. So relative information might just be more important than absolute information. And that gives rise, of course, to the question, can we maybe extend or like do a different types of attention where we include the relative information and we're not using absolute position? And there's two ways or two approaches to where we want to do that, with relative attention and with the rope-based models. So how does it go? In order to understand the relative attention, it's good to have a look again, because how exactly do we calculate this type of attention? If we're looking back, when we are looking how to calculate the attention, what we did is we are comparing the query and the keys and calculating the similarities between all of them. And then we did this normalizing by key in order to, if we have very high dimensional space, to get it a bit smaller. If you now look back, how we calculated the query and the key is both are calculated based on X, on our input, and we just had different matrices which we applied to X. Once we had the weight matrix of the queries, and once we had the weight matrix of the keys. If you do that, it's mainly just a matrix multiplication. You can do some more math around it, how the transpose is calculated. So in the end, you have X transposed, then the two weight matrix, this is an X transposed again. So this is how you calculate the attention between query and key. You have your input X, and then you use these two matrices to calculate. This is now when we're doing it with X with our input. But we're just saying, so typically what we're doing is not taking X as input, but we're taking X plus the positional encoding. So there's like, what we really apply this to, our X looks like as our original embedding, and then added to that the positional information. So that if we're now replacing them, this tells us a bit how this positional information are treated. So our X is the word embedding plus the positional information on top of it. So what does that now mean? You have here the formula, so we can remove the key because it's just like making being a fixed vector. So the attention score is proportional to this thing we had before. So X tilde plus P transpose WQ transpose WK and our X again. And now you can separate that again, because you can remove the brackets. So what you have is here, so first you have the attention, which is only based on the content. So it's X transpose WQT WKX. So this is just based on the content. Positional information are not included here at all. Then you have the second term where you consider the position of the keys when comparing it to the content of the query. You have the position of the query when comparing it to the keys, and then you have the relative thing about how the different positions are important to each other. This is just how it's currently done. And based on that, you can now, and that's what relative position is, they are looking into, how can we change that to not considering our positional representation, but doing it using a relative position. So in that case, we are not putting our positions into there, but we are changing how we calculate our scores. So here we are not really considering the positional information in the attention calculation. It's somehow put into our P, but of course it's considered. So now we can do that explicitly and take our original X. So the first thing, we're keeping exactly the same. The one thing we're doing now is we're changing the other three terms and replacing our P, which encodes the general position information, by now information about the difference between the two positions. So now no longer the absolute position is important, but always the difference between I and J is important. And we have two more matrices, two more vectors. So have a look at each of them in detail. So what we are doing is we are first having our I and G again, but what we're mainly doing now, we are not encoding, we're still encoding that the same way with our senoid metrics, but we're now no longer encoding their position, but we're encoding the difference between the position. So while before you would like to take this function to encode position 3, now you're encoding there like 3 minus 2, so you would encode 2 to say that you're currently at position 2, and that the difference is 2. And therefore, here no longer in your calculation of comparing the query content to the key relative position, you're no longer considering the absolute position of this key, but you're only considering the difference between the query and the key values. Then maybe it's a bit surprising when we are talking about the query, we replace it not by a matrix, but just by some learned U and V. Why are we doing that? The query, when we're doing the softmax, we're anyway normalizing. And therefore, like there, we're always comparing to the same query. So we're also always comparing to the same position. And therefore, it doesn't really, it's more like a bias term. It doesn't make sense to really have there the positional information because the query is fixed for all of them where we normalized. If they are always like something bigger, then they're all the same for all. That's why for the query position, we're just learning a bias U and V. And then for the key position, we are again using our positional information, but again, not the absolute position, but we are taking the relative position, which we're using there to compare. Yes.
What is WR?
W, where? WR?
After V.
Good, that is wrong. That should be K. Sorry, thanks for spotting. So it's yeah, it's always a weight matrix of K because we are multiplying it with X. So this should be K, here it's K, here it's K, then here it also has to be K. Yes, sorry, no, was a mistake. Any other questions? Good. Besides that, there's another way of also encoding relative position information, and that is called rope. And that is what we will look next, and which I think is currently even the more commonly used thing. Here, the idea is when we are multiplying, so again, we are looking at the attention calculation at each layer, where we are comparing our query to our key. So we are doing this multiplication of query and key. And there we have, the query is based on our content XM and based on our information M. And then we have for both. The hope is, can we now find a function like f, so this product between the two of them is depending on M and on the difference between both of them. So that when you multiply the transformation of the content and the position to the transformation of the other element, you get a function which depends not on the absolute value, but it only depends on the two contents and on the difference between both of them. And the nice thing is there is something like that, and that is mainly a rotation. So what that means is we're splitting our n-dimensional vector now into small two-dimensional things. And the main thing is that we are rotating them always in different things based on the position and an initial angle, and then we're rotating more, and that is then our encoded. Because if you then multiply, you're multiplying the rotations, and then the important thing is the difference between the two rotations. So let's do that step by step. So here you have your queries and keys. Yes? And now the first thing is you split the query and keys into two-dimensional vectors. And then you have in total d-half two-dimensional vectors. So if you have a 500-dimensional vector, you can split them into packs of 2. So you have 250 packs of always a two-dimensional vector. And then you're taking this two-dimensional vector, x1, x2, and you're taking the position m. So you have once a vector here, and you have the position. So first is position 1, and so on. What you're now doing is you're rotating this vector by some degree theta 1, and that m times. So if on position 1, you're rotating it once, on position 2, you're rotating it twice, and so on, the more and more you're rotating. And then you get, after you rotated this vector, you get the new, your new coordinates, and these coordinates are then stored. So that's your position encoded. And now you hopefully directly see that, yeah, depending on the position, I rotate more or less, and therefore this is then important. And how are you doing that? So what you mainly do is, for the first two dimensions, you see, for the first two dimensions, they are interacting, 3 and 4 are interacting, because you're always putting them into. So the first dimension is x1 cosinus m theta 1 minus x2 sinus m theta 1, and the second one is x2 cosinus m theta 1 plus x1 sinus m theta 1. And that is exactly, so this first two columns, that is a rotation of the vector x1, x2 by m times theta 1. That's exactly what we want to do here if you do this rotation. And then we do for each our packs, and that is then our new vector, which we can then use in the self-attention. And of course, this is then something you have to choose. What are all your thetas here? So the d half thetas, they are your vectors which you use to rotate. Any questions about this? Yes?
Yes, how exactly do we choose the theta side to configure?
I mean, we can either learn it or predefine it, but this is just to encode our thing, so that we have to set independently.
Our model, then.
Our model, yes. So that's nothing you can define, yes. Any other questions? So the idea is, again, you're doing this relative information by having rotations in different degrees. And it's important, of course, to have different things, so that sometimes if you would do a degree of 1, after 360 positions, you're back. If you do like 90-degree rotations, you're back after 4, and you have very different ones, then when you are back, it's always very different. So your positions are really different also all the time.
But the advantage of the rotation is what compare with the relative position.
The
advantage.
Oh, the advantage. Good point. So, I mean, they are both there to encode positional information. I'm not sure why people nowadays more use. I mean, they're both there to do the positional information. Why this is currently more successful than the relative position, I have to check. I don't know exactly, I have to admit. Yes, that's a good point. No, I didn't think about that. Yeah. So it's more like I know that this is successful currently and more used. I'll check why it's like, what is the main benefit compared to the, it could be that it's past this type of calculation than the previous one, so that this could be the main advantage, but I will check. Good. So with this, we're then coming to the last part, where we want to talk about the what is called flash attention. And this is not about making the attention better, but one major limitation in attention-based models is the time it needs to do the calculation. So although it's like optimized already, still, I mean, that also leads that we want to have longer and longer contexts, so longer sequences processed. Originally, it was done on sentence models, so you can think of sequences of maybe 30 or 40 items nowadays, if you think about or read about large language models, they have context of 2000 tokens or something like that. If you want to there do the self-attention, things get more complicated. So you have to think how to optimize it. And there is different ways of doing that approximately. So how you can like not do the correct calculation. The interesting thing is here we'll want to now look where we try to use the hardware to do things exactly but more fast. The problem is that there's two things. First is that it's both the runtime is quadratic in the sequence length because you have to compare each query to each key, which makes it quadratic in there, and also means you have to store all of that. That's mean also your memory is quadratic. And the question is now, how can you make things faster? Of course, maybe the first intuitive thing is to think, we are doing less calculation, we're approximating things. The interesting thing is, but that this softmax is somehow memory bound. So it's mainly there, or like one main limitation is not the number of calculations you do, but how much memory has to be transported between all of them. And since if you often have to do a lot of memory transport, reading and writing memory is slow, and that's why things get slow. And that's why people looked into this flash attention, and you see here attention for GPT, you see that there's a significant speed up compared to the original one where you had to do the maximal, the masking, softmax, dropout, and then again, which is all like somehow fused into the attention. And there we want to have a look now how you can do that and how you can like make use of the hardware architecture to make things more faster. And the motivation is that you want to optimally use your GPU memory. And there again, have a look at how the memory is used. So you have typically, of course, the CPU memory. When we talked about that before, we saw that we sometimes have to offload things to the CPU. But if the GPU, we have different speeds. You see, you can do like with something like 1.5 terabytes per second on the GPU HBM, and then there is smaller memory like 20 megabytes, but therefore you're like 10 times more than 10 times faster on that. So the question is, do we always have to move the memory back and forth between here, or can we somehow run only here and therefore be somehow more efficient to do that? In order to have a look at that, how is the normal default flash attention is done. So what we mainly have is we have our three matrices Q, K, and V, and these ones we have in our HBM memory of the GPU. What we then do is we are loading Q and K blockwise from the memory. We're computing S equals Q and K, and then write them back. Then we are reading S from the memory, compute the softmax, and write it back. Then we are loading P and V by blocks and write them, calculate the output, and then write that. And then we're reading. Why are we doing this? Like only reading parts already, we can't maybe fit everything in memory. So we have to do the matrix multiplication blockwise because we can't do everything in total. I guess one thing, how to make things faster is a bit obvious. What is the aim, or what would we like to do to make things faster? It's written like that. I think it's what seems to be happening here quite often.
Reading and writing.
Yes, exactly. So we don't want to always write and read it back to the HBM, but can we just do the calculation in general? And that is what is called the operation fusion. So instead of like going like reading it on from the memory, doing the compute, writing it back, reading it again, doing the next computation, writing it back, and so on, it might be nice to just do everything in one thing. But the challenge is that not all our matrices will fit into the memory. So we have to somehow do this in a somehow efficient way. We'll even have to do a bit more computation, and then we can do this thing in a more efficient way. And the overall idea is shown here, and we'll go into a bit more details then soon. So what we have is we have our queries here. We have our keys on top. We have our values, and then we want to have the final output. So what we are doing is we're taking some queries here and some keys from the top, and we are calculating the similarity between them. Then we're getting here the similarity values. What we have to do is we have to write them down, and somehow we have to do, no, the problem is now, before we can now compare them with our values and then do the matching between the key and value multiplication, we need to somehow normalize them, because we need to normalize them over the whole column. And that, of course, is a bit of a problem, because before we can write things in there. If we're only like comparing the queries currently with some part of the keys, we're not directly knowing, like, because you do the softmax, you can't do the comparison to all of them. And that is then, yeah, leading to a problem there that we haven't compared to everything. So the problem is the softmax, where we have to do the normalizing over the whole column in order to do that. How can we do that better? So we have now one fixed query, and we have the first keys which we calculate. Then you do the query key comparison, and if this would be all keys we need to compare to, what we would do is we would calculate the exponential of S1, this is this value, then we would sum them up, and then our final output is the attention value we had here divided by the length. That will give our normalized score, A1 divided by L, and then we will multiply by B1. So this is, if now all the keys are in our matrix, this would be all the calculation, and we would be done and finished. The problem is now that if we have another key, how can we do this calculation? Because then we also have to change this one, because here we have normalized by the length. And that's where we're doing here now. So then we take the next keys here, and we are again calculating Q times K. That's saying how similar these queries are to these keys. We are calculating the exponent, and then this times normalizing is our previous normalizing one plus the sum we're having there. So for the new keys, we can now calculate the correct value. So that's here the second part. For the new ones, we are just taking our similarity, normalizing them, and multiplying with W. It was V, sorry. So that is fine. The problem is, what are we doing here in front? Because there we now know that we used the wrong normalizer. We used L1 to normalize, but to be like across all of them, we would have to normalize by L2. What we're doing is we're just renormalizing our previous output before adding them up. Because if you do this additional normalization, you have now in total, this O1 was calculated like this. This was O1. So if you now see that L1 and L1 is here, can be reduced. So in total in front, you have A1 divided by L2. So then it's again the same as here where you have A2 divided by L. So by rescaling our previous output before adding it, we can like add always things up, and we don't need to store everything. So this where we can calculate our attention. These O2 is now the correct attention of all the queries in Q attending to the keys in key 1 and key 2, using values F1 and L2. So what you can now do is by doing this type of algorithm, you can go like over by your queries and by your keys. You only have to look at each query once and each key once, and go and fill up this matrix one by one. So you don't have to do all the loading, because you're not just adding up as you would do maybe intuitively just the ones for the V1 and V2, but you're like calculating them in between and then rescale. And you can do that over and over again. Now you can do, even if you have case 3, you have to rescale O2 and add then O3 to it, the new V3 aligned to it. And yeah, so then you can do this block over and over and fill this table or the square there. So you do even a bit more calculation. If you see here, this is like some extra calculation you do here, but it's constant. But then you can like only load always a block, and in each block you do the whole attention calculation. You don't have to load and unload some parts over and over again. And yeah, so this is typically used if you're using any attention or transformer library in PyTorch or so. I guess in most cases they will use attention. So the nice thing is everything is correct. So we didn't do any approximation here. So you do the correct same calculation, but you can train these models more efficient because they are like fusing the operation and you have less read and write operation. Yes.
Do the gradients have to be recomputed like a normal?
I think in this one, yes, you also have to recompute because you can't store everything, but you can recompute then for the gradients, you can recompute the activation only of the current block and then do the propagation there also. Yes?
We do the code compute O in parallel because we compute O2 needs O1.
No, you can't do that in parallel, but this is like, I mean, you're doing your O and V maximum so that your memory is like full. So anyway, your GPU is somehow busy doing that. So the Q is not one single query. Q can be a set of queries and K and V also. And then you're running all this, and then you're loading and uploading again. But so yeah, you're right. You can't now distribute it over three kernels and do Q1 and O1 in one and the others. What you can do in parallel is you can do it for other Qs because then you calculate other O's. So for other Qs, you could do it even in parallel. Okay, so with this, I hope for today and on Thursday, I gave you a bit of an introduction, overview on self-attention. You understand what self-attention is, how it's calculated, what is the important properties that we can process this in parallel, and that's therefore very, very fast and used. But if you're using it out of the box, it will be position independent, and that you have somehow introduced the positional information either by positional encoding or by relative position information or rope or something like that. And then we looked a bit into how you can speed up things in order, like having things like flash attention, so you can fastly calculate things. Any questions to self-attention? So we'll continue to see that. I mean, for sequence models, it's important. Well, of course, later for LLMs or so. So it's like somehow I would say at the moment the most important architecture. But of course, that shouldn't stop us from developing other architectures. And that's what we want to do the rest of today and then continue next week. And there are the state space models. So give me a second. Okay. Okay. So what are we wanting to do here? What we want to do in the next part is first we want to look at why should we care about it? What are the challenges of current other architectures and how we might be able to address them? And we will do that, especially looking at those self-attention and RNN CNNs, and maybe think if we can somehow take advantages from all of them. And then we want to look at three different types of models of that are the linear time invariant, the linear time variant ones, and the continuous time state space models. A famous example of this last one is what is called Mamba. It got quite some attention in last years, and it's a bit like the other type of architecture people are looking into at the moment, especially to speed up things and being more efficient we'll at the end also look a bit at efficiency. But yeah, since language models are very successful with transformer-based architecture, so the first question is, of course, why should we care about it? It's a nice architecture. We're getting surprisingly good results. So why would we be interested in other types of architectures? And we have good advantages to use self-attention. So on the one hand, we have these interactions between all elements, which is very interesting. We can use information are flowing from all inputs to all outputs, meaning that we, for example, have typically not this problem of vanishing gradients, because we can directly use information from the first position from the last, and so on. So we have this interaction between all elements, and they are like highly optimized for training. So we've seen that there is like somehow, yeah, dedicated developed for things like GPUs, so we can efficiently use them on the. So what are the challenges? And we looked at that a bit already, and it's like somehow a continuation of that what we saw in the flash attention. There seems to be some problem that it's sometimes very inefficient. So, and there we have to differentiate a bit between now inference and training. And that's maybe a bit of a look ahead, but I think you can imagine already there's a difference between inference and training in a lot of these ones. If you think about them as a sequence, there's a big difference. In training, you have the whole sequence available. So you put in your whole sequence and can do any type of calculation. Next week, we see how they're often applied also in inference when we want to predict something. It is often that we are predicting something for the next position, and before we have to do the prediction before we get the next information. So in this thing, we are not having everything in parallel available, but we are getting information one by one, and then have to do a prediction. So there we might not be able to use the full advantage of GPUs because we can't do like all the inputs prediction at once, but we anyway have to do it one by one because we only can do the second position once we have the information about the first position. But even in inference, there's a problem. So if you're now doing here this calculation, so as I said, in inference, you can't do all calculations in parallel, so you do your calculation here. If you do the calculation here, you have to take this query and compare it to all the other keys beforehand, then get the similarity, and then calculate the values. If you do that one by one, of course, it doesn't really make sense to every time recalculate what is the key and the value of the first position, what is the key and the value of the second position, and so on. Because these will not change. This is always the same. So you can use a cache which stores you like the keys and values here, and then the next time you don't have to recalculate it, but you can reuse it, and so on. So you only have to do that once, and here you can then only have to do the comparison to the queries and values. But of course, that is nice. You're a bit faster, but still you have to store this query in key cache, and it gets longer and longer with the sequence. So you have to store more and more things. And if you now compare that to the RNN, there's a big difference. In the RNN, you only have to store always the last element, the H, because everything just depends on the H. While here, you have to store the full history, and that might at some point get very inefficient because you have to do this long time storage. That's convincing, or any questions? The same thing is for training, or no, there's a different thing. So in training, you're not storing this LV cache because you're doing always everything in parallel. But still in training, your computation is quadratic in the sequence length. So you have to compare every query to every key. And that again might be computational very, very expensive because you have to do all these types of calculation. And it might be nicer if you not always have to do each query to each value, but you could do there something that can speed things up and you have it more linearly. So The question is, do we really have to always like have to fill out this full thing, or can we store some information that we not have to calculate everything all the time? How is it done differently? So let's go a step back and have a look how these things are done in an RNN. So what would be a wish list is somehow that during inference we have constant time. That's how it's done in an RNN. So there you don't have to store the whole history all the time. If you're creating things now one by one, you only have to store the last one, and everything is stored in there, and you don't have to do the previous processing. So things are significantly more efficient. Be aware, this is of course a bit like in training, it's differently. There you have here even a bit the disadvantage, because you have to store the history and can't use, therefore can't do all processing in parallel. But in inference, you can't do it based on the nature of your task. So you're all anyway processing one element at a time. And then it's a bit like sad that you always have to store everything beforehand. So that would be nice if we could do like constant memory during inference. And in training, it might also be nice if now we can have the wish list, we can think what could be nice. There in CNN, things were a bit more efficient because we have this linear time computation. You have the fixed size kernels, and your kernel was always looking somehow at the fixed size here. And so you only needed to do this computation. You didn't like have to do more than linear time computation. You didn't have to compare all to all. You only had to like use the current kernel as input into it. So this motivated on, can we somehow, reuse ideas we had from RNN and CNN to be more efficient in that, and maybe stay, or like at least, of course, have the idea, stay somehow in things where the performance is similar to self-attention. And there is one thing which is from a very different area, which is called linear time invariant models. It's more coming from physics, but we'll see that they are somehow related to RNNs. And the first thing is what is interesting, they are somehow merging again CNNs and RNNs, and we'll see there will be processed. We can view them as both, as an RNN, as a TNN, and thereby take some of the both advantages that on the one hand we have efficient training, and on the other hand during runtime have the thing. Maybe a very surprising thing first we're doing. We're now even making the RNNs weaker again, but that only as a first step to do then the things. So how does a vanilla RNN work? The vanilla RNN we had as a repetition, we can formulate is that we had our hidden states here in blue, and the next hidden state depends that you take your previous hidden state, you multiply it with a weight matrix, you're taking your input, you're also multiplying it with a weight matrix, and that is your hidden state. The new one, you're doing a non-linearity on top of that, and then you have your output, which is just taking this and multiplying by C. However, this had some disadvantages. It's difficult to learn, especially the training was in some way also inefficient, because during training we couldn't do this parallel processing. So what we had to do is like during training we also had to go like one by one through it. And we would like to have this differentiation that during inference we're going one by one and only store like something fixed. But during inference it would be nice to do things in parallel. The nice thing is, both good and nice thing, we have the limited memory, but that also means during the calculation things are efficient. Now in the LTI, so the linear time invariant systems, we're doing only one minor change through it, and we're making our model in some way even weaker. So what we're doing is we're removing the nonlinearity in here, in the RNN. So that your new hidden state only is a linear combination of your previous hidden state and the input. And first you would now say, hopefully, this is very weak because it also means we can merge everything together and that can be like compressed into one single model. So that makes things not as expressive anymore. So why would you do that? However, the nice thing is, yeah, if you can merge everything together, is now we'll see we can also do parallelization during training. So even though we are formulating this network this way, we can now formulate it also or view it differently, and then we can do all our calculations, our forward and backward pass in parallel, and don't have to wait for the calculation here to do the next thing. And that is only possible if we have here no nonlinearity between the different hidden states. And yeah, an example of where this has been done is the so-called model S4 in 2021, where that has been done. Maybe, but I mean, to me, the first thing which was surprising and where I was like, why should I do that is, of course, why do you want to remove this nonlinearity? And the main explanation for that is that we want to do parallelization during training. So how does it work? Why can we now do parallelization during training? And that is because we can now use a different type of algorithm to calculate our hidden states here. And we don't have to do it from left to right, but we can do it in parallel. To make things a bit easier, let's take the very, very simple type of network where A, B, and C is all one. What we are then mainly doing, I hope you remember that, we had that already, you're mainly summing up. So if you put in 3, 2, 3, 1, at each position you have the sum up to the partial sum up to this position. We had this example 5 lectures ago where we looked into how you then like how this is an RNN. So this is a very simple example here where you have A, B, and C all equal 1, but it's just to show you how then the calculation can be more similar, because the nice thing is now that we will see that in order to calculate all our hidden states here, we don't need to do it one by one because it's linear now. You can change the order and we can do a more efficient calculation. This is done with the so-called parallel scan and the upsweep and downsweep. Again, it might be surprising, you're now doing things, even more calculation, but you can do them in parallel. So what you're doing is you have your input, which was 3, 2, 3, 1. And what we now can do is we're just doing a parallel calculation where we build a tree where the head is always the sum of both children. So we're doing our input here, it's 3, 2, 3, 1. And now you do your upsweep where you calculate 3 plus 2 is 5, 3 plus 1 is 4, and 5 plus 4 is then 9. And then you have the final hidden state here. Yeah, that was the final hidden state. But we not only want the final hidden state, of course, we need to have all hidden states to do all the calculation. So how can we do that? That is now the second step where we have to do the so-called downsweep. So we're now creating another tree from starting with 0 from top to bottom, and there the definition is a bit different of the pre-scan. So the pre-scan, we start at the top and then we have 2 children. The left child has always the same value as the parents, so it's like here, and the right child has a value of this tree from the left child plus the pre-scan value from the head. Looks now a bit complicated, but we're just going through that one by one, and then I think things get a bit more clear. So at the first position, here the left child gets the same value, which is 0, sorry. The right child gets the sum of the left child is 5, plus our own value is 0, so here should be a 5. Okay, we did a different calculation, sorry. Then we're going here down again. So this one is the same as that. Here it's the sum of the left child, that's here 3 plus 0, so we are doing 3. Now here we're doing, hopefully you remember the 5. We had the 5 before calculated. Now the left child is the same value, it's 5 again. And now the right child is 5 plus the left child on the sum, which is in this case 3. So we have 8. And now you see, you have here, by shifted by 1, you have your hidden states. 3, 5, 8, and then the last one is the 9 you calculated before. So 3, 5, 8, 9 is always the weighted sum. So this way, you can now calculate in parallel your type of hidden states with now the big advantage, you're not having linear time. I mean, if you're doing it for this small examples, I can agree that you're saying this doesn't look efficient. But when you do it in parallel, you mainly the runtime depends on your height here. The height is log. So you have log plus log is 2 times log, which typically is much faster than linear. So you can do it in faster if you parallelize it than linear time. So you can do this type of calculation faster with this type of parallel scan. And this, of course, only works since you have a linear, because you're linear, it doesn't matter if you first sum up 3 and 1, and then 3 and 2, and so on, or if you do 3 plus 2 plus 3 plus 1. If it's non-linear, as before, there would be different values. And then you couldn't do the parallel scan, because then the order matters in which one you do your application. If you have a linear combination, the order doesn't matter, so we can change the orders here and do the efficient algorithm to do the calculation. Good. Any more questions? Oh, it's too hot for too much mass. Good. Another view of that, and that maybe makes things even more clear, is you can unroll these things, and then you're seeing that it's a bit like that's the calculation we did before, and you see that it's then more related even to the CNN. So we said this is our definition of HK and YK. So that means H0 is just B times X0, and then Y0 is C times B times X0, because you're doing HK, H0, and C. As the next position, we're having here H1 is A times this one. So A times B times X0 plus B times X1, because we're at the next position. And then Y is just C times this value, so you put 10. The next time again, so you take A times this value, which means A squared times B times XL plus A times B times X1 plus, and now B times X2, and here just this 2 again. So that is somehow unrolling your network now, and now you're seeing there is no non-linearity in between. So in between here, you can change the things, the order of them. Now you can view this as here, for example, as again more a CNN. To calculate this hidden value, what do you have as a kernel? You have 3 inputs, x1, x2, and x3. And so your kernel, you multiply with a square b, ab, and b. So then now, before we had thought about this as an RNN. Now you're viewing that as a CNN, where to calculate H2, you're multiplying the input x0, x1, x2 based on that. So now your H2 here is independent of the others H. So it only depends on the input. That only works because we have no nonlinearity, but that makes the calculation later faster, because we don't have to wait for H1 to be calculated, but we can somehow do it directly. So you can view that. So your xk is then the long one. So you, I guess, seeing the pattern here, you always have a c, and then you have first a squared, then a, and then no a. So there's always less. So in order to calculate then yk, what your kernel is something cb, cb, cab, c, and c times a to the power of l minus 1b. So it's a bit like you have now a kernel, and that's maybe the big difference to CNN. We don't have a fixed kernel anymore. the kernel now depends on your length, but you can generate always your kernel depends on the different lengths. By having this type of nonlinearity in there. So what we somehow have is we have both the advantage of CNN and RNN combined into one model. So at least from the computation side one. If you're doing the RNN view and really calculating your hidden values, you have a fast inference because you only have to store your one hidden value. You're doing this view here. So you're calculating HK and then you can calculate YK. By unrolling, you can also have this convolutional view here, where you take the kernel, multiply it with your input, and then you directly have your output out there. So that means during training, you also have the fast view, because during training, you don't have to view it as an RNN, but you can view it as a CNN and do these things in some way very, very fast. So this seems to be, in that way, at least in the first way, quite nice. Are there any questions to these two things? So to keep in mind or to remember, it's somehow very similar to our original RNN. The main difference is that we don't have a nonlinearity here, so it's just a linear function, which means during inference we can do it fast because you just always have to stay one hidden state, not all the ones, only the one. And during training, we can reformulate it with unrolling into like a CNN style kernel and do then also the computation fast, because we don't have to calculate all the previous hidden states to calculate the new one, but we can directly calculate the influence of all the inputs to the current model. Okay, so is everything great? Of course not. I mean, one thing for example, we had as a big issue before is that we had the vanishing gradient problem. And that is here, if we would use it somehow the same way. And it's even like you very nicely see the problem here now, because we had defined here the kernel. You remember that, how you define the kernel, and you now see, oh yeah, you're always multiplying here with A, always with the same time. So it's becoming quite clear that this might be an issue in the derivation. If you always multiply with the same way, we saw if it's a bit higher than one, it's getting a problem. If it's a bit lower than one, it's also getting a problem. So we somehow still have here our vanishing gradient problem. Also, the computation might be complex, which means in order to calculate the kernel here, we have to do n square times for the multiplication, for one matrix multiplication, that L times, and that might be also quite inefficient. There is one parameterization of that which seems to work quite good, and which was used in the S4 model. That's a so-called Hippo matrix, where the matrix is then defined like this. So the diagonal is always n squared, and then you have values above and below it in your matrix A, and you have the matrix B. The idea here was that there's like mathematically proved that they try to find the matrix which tries to store your previous signal best given the limited size. So of course you cannot store any previous signal, but you can store it. You can try to show like this matrix does it very well. So that's why this type of Hippo matrix is often used. We won't go into details of how to do that, but that is a bit idea of doing that here. Maybe one thing I didn't mention, we'll come to that later, but what is there, because I said here continuous signal, until now we always have discrete signals. And especially in this idea of linear time invariant variant models, there's often also, instead of defining it, the RNN here in the discrete space, and you will always, if you read the papers, and we'll can't do that a bit. You'll also like try to define that in a continuous way so that ht is a function. And then in this case here, it's defined with a derivation. So you have a derivation equation here in order to define your functions over time. And in this case, this Hippo matrix would be optimal. So that is one way of you're doing it. But in generally, it's a problem with this type of models. And that's what we want to look. Why is it not maybe the best? So first, if you're doing this Hippo-based matrix and using the matrix, one interesting thing is that for a lot of tasks where you really need long information, it's working quite well. So this is a performance of, in blue, a transformer-based model, and this S4 model, which does this type of linear RN answer, and you use the performance. And you see that, for example, Pathfinder, not surprisingly, is something where you have to like find a path in a matrix. There's like very long-range dependencies. There's list of, so there is some type of very interesting problems where you have very long sequences, and in these long sequences, this type of model seems to work very well. So there seems to work well to model long-range dependency, and therefore, of course, it might be also very good for using text or for others. However, if you then compare that on text-based models, so these are attention-based models, and then you have 4 different models which all are somehow based on this state-space models. What you have here is different types of parameters. So you have a large version of that, all at least similar, and the same thing for the attention. What you now see is, yeah, if you look into how fast they are, these are typically all faster than the attention-based. So it seems to be a very efficient way. However, if you look at the performance in text, so here it's perplexity, how good can it estimate text? We're seeing that it's still not working really better, or it's significantly worse than attention. So here you want to have as low value as possible. It's perplexity, and you see that all the values are high. So these state space models seems to work well for long-range dependency, where there's typically some clear structure on that, they can solve them, but when processing text, they seem to have still some open questions where it's not clear how we can best use them. And the question is now, of course, so what is missing? Why they might not be working so well in order to do that? And there's 2 things which in the RNN is done again, or in the time invariant model is done again, which was already a problem in the original RNNs in a way. And this is especially important for like text processing. The one question is about filtering. So when we're doing this, we're multiplying our xk with b, which means all inputs are treated the same. So we're just taking an input and multiplying it with x. So all inputs are treated the same, which means, for example, you can't easily try to model that you ignore some input. If you think about text processing, it might be always that some text is like unimportant. So you want to have a model which can just go over it. In the attention, you could easily do that. You can like say, oh, I don't attend to that. You can just skip over it and ignore it. In this type of model, each input here is always multiplied with b. So it's not easy to say, oh, these ones are unimportant. I want to. For text, this might be important. For image, I guess you can also imagine that that might not be the best. So there's several, or for audio, if you think about it, if you want to listen to something, there might be some noise in between. You want to have a model where you can at some point just say, oh, let's ignore that and don't deal with it. And there's a second thing, which is also for this type of thing may be important, which we can't do in this type of models. And the second thing is that we can't easily like reset the history. So just imagine again, you're like putting in there a long list of text. And then you would like to have the opportunity that at some point, based on your current input or so, you can decide, oh, now some of the history is no longer important. I'm now going into the neural networks lecture. For the next time, it's not so important what was happening during lunch. I can skip that. Maybe I need it later, but it's not as important as before. So you want to have the possibility to, at the beginning of a thing, start a new context. Or if you remember what we saw about the LSTM, there it seems to have to be important. We have these neurons which look only at the quotes. So there you would have to have some ability that, okay, now I'm in the quote, so forget what happened before. Now I just want to remember that I'm in the quote, and then somehow you're out again, so you can just forget everything. And this is not here really possible, because what we're always doing is we're taking our last in state and multiplying it with A. So there is no control on like, oh, how important is our history? Is it maybe depending on the current situation? Is maybe the history less important or more important, so that we are not continuing to do that. And of course, these two choices are a bit selected. So this is now something that we will look into how we can use them in linear time variant systems in order to like address that and not treat all histories and all inputs the same, but like somehow control it so that we're only doing them. But this one we'll then do in detail on next Tuesday. As there's more questions, we can do them now. And if there's no more questions, then I'll see you again on Tuesday.